Let's go. Okay, we're back in business. All right, so this is where we are now before the break. You know, you realize that we need to know how to use the plastic section modulus, and this is where it's going to occur, you know, when we are beyond the first yield. Okay, we are in this zone, and when we are in this zone, we are going to focus only on the full plastic. Okay, we are not going to try to solve anything, you know, where we are about to reach plastic. And we should know that when we reach the full plastic, this is your stress distribution. Okay, and two things we are going to use to help develop our plastic section modulus is right? Two things: the internal and the external equilibrium. So let's take a look at the internal equilibrium first. You know, this is your stress diagram. One is compression, one is tension. So we know if we focus in this direction, we can say our sigma Fx must be equal to 0. Simply put, tension force and compression force in your cross section must be equal. Okay, if they are not equal, it means you don't have internal equilibrium and you're done. Okay, so to have that, I can say that tension must be equal to compression. Okay, maybe it's better if I go out and use this page. Okay. Oh. Okay. Now to achieve equilibrium, we have to say that whatever the cross section we have, the ugly shape like this, you have compression and tension. The compression must be equal to tension. Okay, and the force here, because the stress is like a block, you know, it's Fy throughout. So I can say that Fy multiplied by area under compression must be equal to the Fy multiplied by the area under tension. Now, generally, if you use the section with one material, it means that these two Fy are the same. So it goes. So to achieve internal equilibrium and you have only one material, it's safe to say that the area that takes compression must be equal to the area that carries tension. Now this is true when one material is used. So what we learn from this is that you need to find the axis where you can achieve the area under compression equal to the area under tension. Okay, so let's say if you have the irregular shape like this or like the one I just drew, we need to find the line that separates the area of the cross section into two equal area, and one under compression, one under tension. This axis is called plastic neutral axis, or PNA. Okay, if you can recall, when you calculate your elastic section modulus, that is based on elastic behavior, you can use I over S. And when it is S, this is where the neutral axis is, right? And that is called elastic neutral axis. you can locate this elastic neutral axis by finding the centroid of your cross section. Okay, it is at the same location as the centroid. So if you can locate the centroid, you can locate elastic neutral axis. But for the plastic neutral axis, you need to find the axis where it separates, where it divides the area of your cross section into two equal areas. One under tension, another under compression. Okay, now after this, we can proceed to take the external equilibrium, and the moment inside must be equal to the moment outside. We can say that. Okay, so I'm coming back to this. Okay, to take the moment here, and then it must be equal to the external moment. We have the force here, right? So we need to take the moment with respect to this plastic neutral axis. Okay, I can call this distance yc, and then I can call this distance yt. So my internal moment will become Fy area compression multiplied by yc plus Fy multiplied by area under tension multiplied by yt. This has to be equal to the external moment. Okay, and again, when one material is used, it means that we have one Fy, so you can pull Fy out, and you have AC, excuse me, ACYC plus ATYT equal to moment. And let's give it a name here. This, ladies and gentlemen, is the plastic section modulus. Or you can simply say it is the summation of the moment of the area about the plastic neutral axis. Okay, so you can come back here and take a look. Okay, well, I use the word stress here. Fy is the same, and this is, officially called the summation of AIYI with the absolute value. And you may call that plastic section modulus. Okay, if you can locate where your plastic neutral axis is, you can sum the moment of the area about plastic neutral axis. You will get plastic section modulus. Is there any question? Okay, and the summary is that if we talk about My, that's the first yield. This is equal to Fys, or I have a sigma here. It's the same as Fy multiplied by elastic section modulus. This My is with respect to elastic neutral axis. Okay, that stands for with respect to elastic neutral axis. And then you can have MP when you keep the loading going, and MP is equal to Fy multiplied by plastic section modulus. This is with respect to plastic neutral axis. Okay, generally, if we have doubly symmetric section, okay, the plastic and elastic neutral axes are at the same location. So you don't have to bother looking for it. But if they are not symmetric in either shape or the material you use, you may use more than one material, you need to locate the plastic neutral axis. Okay. One more thing you need to know is that once you reach My and you can continue on to load your beam until it reaches MP, this is where you may call it a reserve strength once the first yield occurs. And we have the way to identify our reserve strength by calculating the shape factor, which is MP over My. If you have one material, this may be written as Z over S, correct? Generally, if we have the H shape, this shape factor is approximately 1.1 to 1.18. Okay? Is there any question? Now, as I said before, you can say that if you have a symmetric section, your elastic neutral axis they are at the same location with the plastic neutral axis. But if you have the non-symmetric, you're gonna have to locate them. Okay? I think the next one will be about the local buckling. So that's it here. Do we have any question? Do you? Generally you don't. So let's start with our example of the calculation. Okay, so we are going to use this one, CV 341 steel design examples, and we are going to start working on example number 7 today. Okay, pardon me, I still have that from the previous example on it. I hope it doesn't bother you. Okay. You know what? Before I do that, let me show you before I start doing example number 7, let me work on a simple rectangle to show you what's going on. Okay, so let's work on a rectangular section first. Okay, so let's say I have a section with the width B and the depth D. Okay, generally, let's focus on the x-axis. Okay, now this one, elastic section modulus or S in x-axis can be calculated from Ix divided by C, which is D over 2 in this case, right? And Ix, without further ado, is BD cubed over 12. So Sx generally is BD cubed over 12 divided by D over 2. So that's 2, that's 6. So you have BD square over 6. That's the elastic section modulus of any rectangle. So keep that in mind. Okay. And likewise, you know that this is a symmetric section, right? So you know this is where your elastic section modulus is, and incidentally, your plastic section modulus as well. So when you are going to calculate your plastic section modulus, remember it is the moment of the area under compression and tension about the plastic neutral axis. So that means you are obliged to divide the area into 2 areas, you know, one compression, and you may say, okay, tension. Let's use the blue one. So you have two areas. So plastic section modulus now. It is Zx, which is equal to sigma AI yi. Okay, so in this case, it becomes, the red area is how much? All right, no response, thank you. So it's B multiplied by D over 2, correct? And then the moment arm, if this is D over 2, the moment arm becomes D over 4. And for the area under tension, it's pretty much the same, you know. B D over 2 multiplied by another D over 4. Which means that in total you have BD squared over 8 and then BD squared over 8. So it is BD squared over 4. So these two formulas are the ones that you can always use. You know, this is the elastic section modulus for any rectangle. And this is plastic section modulus for any rectangle. Now remember these two very well because you may run into it again soon enough, and we are going to use it again in this class. And that means if I calculate the shape factor of a rectangle, it is MP over MY. And so it is ZX over SX. So it is BD square over 4 divided by BD square over 6. That is 1.5. So that is the shape factor of any rectangle, 1.5. And remember, the plastic section modulus is always the, you know, the summation of the moment of the area about the plastic neutral axis. So that's why we divide the area into two areas and then take the moment about the plastic neutral axis. But this also gives us the typical formula for the plastic section modulus of a rectangle. So if you find a rectangle that shares the centroid with the plastic neutral axis, you can use this formula right away as well. Okay, is there any question? I suppose not. So we can go back and start working on our example here now. Okay. Now this is what we call a build-up section, ladies and gentlemen. It will be made of two plates for the flange, this one and that one, they're equal, and then another plate for the web. So we are going to calculate the MY, MP, and shape factor of this H section. Okay. So we're going to start with the strong axis first. Do I need to show you how to calculate moment of inertia? Well, let's do it one time, okay? In x-axis, that's this axis, right? Strong axis, x-axis, or strong axis. Ix is going to be equal to the moment of inertia of the flange. You know, the unit is in millimeters, but I will work in centimeter, okay? So I will work in centimeter. So we have that flange Generally, you can say the moment of inertia of the flange itself is 15 multiplied by 1.2 cube over 12, right? But this is 1.2 power of 3. So I say, yeah, it's pretty close to 0, so I don't care. Negligible. So for those of you who have to be precise all the time, will go crazy, but I don't care, okay? The moment of inertia about x-axis of the flanges generally come from the AD square term. That is the area of the flange and then multiply with the d distance, which is the distance from the flange centroid to the centroid of the cross section, right? And that is equal to half of the web plus half of the thickness of the flange square. And we have two flanges. We multiply that by 2. And then we have the web, which is equal to b d cube over 12. So let's say generally this is about 22300 centimeter to the power of 4. And elastic section modulus is therefore equal to this divided by, be careful, it's going to be this divided by 2 plus the total thickness of the flange now, right? And this is roughly 994 cubic centimeter. So that is your elastic section modulus about x-axis. Now let's do the zx. Now zx is equal to the summation of ai yi. So you can have a choice of, you have two flanges and you can divide the web into two webs as well. So I can do that, and that's going to be equal to one flange, that is 1.2 multiplied by 15. Let's write the same way as the both. 15 multiplied by 1.2, so area the same, Now you have the distance, which is the same, half the web, 42.5 divided by 2, plus half the thickness of the flange. This is AIYI of the flange, plus the web is 0.8, because I'm going to use this formula. So that means I need to divide the area into one compression and one tension, right? So that becomes 42.5 divided by 2. And the Y bar is also 42.5 divided by 2. Okay. And this entire thing is only for a half. So I did a bad job. I ran out of the area. So this entire thing must be multiplied by 2. Okay. And that is equal to, let's say, 1150 roughly. You can also not do this. You can also do this, or Zx should be equal to the flange, right? You have two flanges, and then the area of the flange is 15 multiplied by 1.2, and the distance is 42.5 over 2 plus half the thickness. So we have two flanges already, but for the web, it's basically a rectangle that coincides with the plastic neutral axis. So I can also use the formula BD square over 4 for the web right away. That is my B. My D is 42.5 square over 4, which is incidentally, you know, it's the same. That should be over 4, right? Not 2, sorry, right. So the arm is over 4. That's why when you multiply by 2 here, it becomes exactly the same as that. And that will give you the same answer. Okay. So we have Sx and we have Zx. Generally, because Fy is the same, so I can go on and calculate my shape factor about the x-axis right away, which is equal to 994. Oh, sorry, my bad. Zx over Sx, which is equal to 1150 over 994. That's about 1.16. So that becomes the shape factor in x direction. Okay. Now let's do the weak axis. Here we go. But the weak axis is incidentally, it's like you are doing this beat. But this axis is this one, right? Hope it makes it easier. And again, IY. I'm not going to include the web because it's so thin. So my IY basically just the 2 flanges. To B, it's a thickness, it becomes a thickness, right? So it's 1.2. And the depth becomes the width of the flange, 15 power 3 over 12. So that my IY, which is equal to 675 centimeter to the power of 4. Okay. And my, that's means my SY is equal to 675 divided by 7.5, right? A half of this. So that's, ladies and gentlemen, that's 90 cubic centimeter. Now, the plastic section modulus in y direction then, so Zy becomes, again, just this, because the web is nothing. So I can say that this is a rectangle, right? So I can use my BD square over 4. So B is 1.2, D is 15 square over 4. The web is negligible, so I'm not going to do it. If you want to do it, it's fine. Or, you know, let's say, you want to see how it goes, you know. If you want to consider it for the flange, for the web, B is 42.5, right? And you have 0.8 cube over 12. So 0.8 is already less than 1. And you multiply with itself like 3 times. The number dwindles down, so it's, you know, pointless. And for this as well, if you, because this is another rectangle, correct? So it's B D square over 4. So, you know, both of these terms just, woo, not worth it. All right. Let's say now Zy is equal to 135 cubic centimeter. So I can calculate a shape factor in y direction is zy divided by sy, that becomes 135 over 90 or 1.5. Wow, isn't that the shape factor of a rectangle? Yes, it is, because when you look at the weak axis, when I flip the beam into this direction, you can see very clearly that this is nothing more, nothing less than a series of rectangles, you know, put together and lined up in one axis. So in weak axis, it's just nothing more than a rectangle. Okay, so we are done with that. Is there any question? So that means no. Okay, oops, sorry, wrong script. Gotta stay with this one and try to do the, you know, not so symmetric section. Okay, so now when you have this, you need to locate both elastic and plastic neutral axes, right? So what's gonna be? I think we're gonna need to do some calculation, but it should not be beyond your capabilities, right? So the gross area is 12.5 multiplied by 2.5 plus 20 multiplied by 1.9. That is in total of 69.2 square centimeter. And you can calculate your y bar, right? And to calculate your y, oh, what is this? Okay, we're back in business. To calculate your y bar, generally I prefer to take the moment, say at the flange, to eliminate one term from my calculation. So my y bar is equal to 2.5 over 2, right? That's a distance from top to the centroid of the flange, and then plus, because I take moment at the centroid of the flange, so I eliminate the flange itself. So it becomes just the stem, right? For the T, we don't call this the web, we call it stem, okay? So just the stem, the area is 20 multiplied by 1.9, and the y bar becomes half of the flange thickness plus,
Sorry,
yes.
did you just write on the screen?
I write on my iPad, yes.
But it's not shown on the screen at all.
At all?
Yeah.
But it shows on my computer screen. You guys can't see?
Okay.
Okay, let's redo it, okay? Let's hope it shows up. Okay. Wow, that can happen. Anything bad can happens. Okay? Can you see it now?
Yes.
Okay, so I'll give you a minute or two to catch up, okay? Thank you for letting me know. If you remain quiet, you just see the blank screen, I suppose. Okay, let me know when you finished, okay? Don't just let me sit here like a few minutes like a madman. So basically, that's the gross area, okay? And I am calculating the y bar to locate the elastic neutral axis. But I take the moment at the centroid of the flange. Okay, so so I eliminate the flange term from my calculation. So this term y bar, you know, coming from the top is just equal to half the thickness of the flange. This one, and then I take the moment with just the stem. We call it a stem. So it's this is the area of the stem plus the distance from the top, which is I mean the distance from the center of the flange, which is half the flange plus 10. Okay, and then divide by the total area, which is 69.2. That gives me roughly 15.02 centimeter from top. Sorry, that's the wrong one. I actually, in my note, I did it from the bottom. So excuse me, it's not right. Hang on a minute. So it's from the top, it should be 7 centimeters. Okay, roughly 7 centimeters. .5, more like it. Okay. Now, you guys are catching up? Huh? Are you guys catching up? No, nobody is telling me anything, so I suppose that's a yes. So the next problem is how are we going to locate the plastic neutral axis? So generally, the elastic neutral axis is roughly here. Okay. What about plastic neutral axis? How can we know whether it's in the flange or it's in the stem? So, you know, generally you can make comparison between the area of the flange itself and the area of the stem. Remember that the plastic neutral axis must be the line that divides the cross-sectional area equally. So with a quick look, you see that the area of the stem is about 38, correct? 1.9 multiplied by 20, that's 38. I can write it down for you. Area of stem is 20 multiplied by 1.9, that's 38. So which is more than, it's not easy. Square centimeter. This is more than AG over 2, correct? This is more than half of the area. So that means if you are going to have the plastic neutral axis that divides the cross-section equally, it must be in the stem because the area of the stem is way more than the area of the flange. So with this, you can assume that let's call it YP in the stem. Okay. You can say that your YP is coming down from this. Okay. Let's be consistent with what I did before so that I don't give myself a terrible headache. So let's call this distance YP. Okay. So somewhere there is the plastic neutral axis, which divides the area equally. So I can say that if this is true, I would have the area of the flange plus some portion under YP. Oh, again, you know what? I am so sorry. Let's do YP again one more time so that I can be consistent with myself. My apologies. Shouldn't hurt much. Okay. Okay, let's clean it up a little bit. It's better. Actually, YP, to do YP, it's actually you go up. It's easier. Okay, let's call that YP. My apologies. So if that's YP, it means that the area, left in this is going to be equal to 1.9 and then 20 minus YP, right? And then because of the equilibrium, the area under compression, which is this, should be equal to area under tension, which now becomes 1.9 multiplied by YP. And we can solve this, and you get your YP equals to 18.22 centimeters. You should go back and check, and you see that my YP is actually less than the length of the stem, which is correct. Okay, so that's it. You now know where your YP is. You know where your elastic neutral axis is. You can just go ahead and calculate your elastic section modulus and plastic section modulus. Okay, and I don't think I need to do that for you. Is that okay? Hello? So you can just go on and do it yourself. Can you do that?
Okay.
I can do plastic for you. But I'm not gonna do elastic for you. Okay, I'm too lazy now. You should be able to do the elastic by yourself. So Zx is going to be equal to, let's say, before I do this, let me try to draw a picture for you. So you now have this piece. You now have that piece. That's your plastic neutral axis. And you now have another piece here. Okay. This piece is 18.22. So this piece is 1.78. That right? And then you have the flange. So that means your Zx is now equal to, let's take it one by one, okay? And you don't need to hurry to doing anything. You just keep calm and draw a proper picture. It's piece number 1, number 2, and then number 3. Okay, so let's do number 1 first. Number 1 is going to be equal to, the area is 12.5 multiplied by 2.5, correct? And the distance will be equal to half from the flange centroid. That's 2.5 over 2 plus 1.78. The second one is this one. So it is the, let me begin with the thickness first. So it's 1.9 multiplied by 1.78 and then 1.78 over 2. So you can see that this term gives you rather something like WL squared over 2, right? So yeah, you bet it's like that. So the third piece is 1.9 and then 18.22 square over 2. So that becomes your plastic section modulus. All right. Is there any question? Question, folks? I'm gonna count to 3. 1 and 2 and 3. So there is an oops. I don't have the number with me, so you guys can do it yourself. Okay. One crazy thing about a section like this is that your maximum elastic section modulus can be greater than plastic section modulus. Okay, but when we consider the first yield, you should use the minimum elastic section modulus. All right, not the maximum one. Okay.